So for our last practice problem, we have this question, and it says that the production of gold during the California gold rush between 1848 and 1888, the production of gold can be modeled by this function here, G of t equal to 25t over t squared plus 6, where t is the number of years since the rush began, with t being between 0 and 40. Notice that we have a closed interval, and that this interval right here is going to be continuous. And I can tell that it's going to be continuous right away looking at it, because this t squared plus 16 is never going to equal 0. And I can't factor it. It's not going to cancel with anything in the numerator, so I have no holes in this graph. I have no asymptotes. This is a nice continuous function. So this problem is asking me for the maximum amount of gold. So we're looking for the absolute maximum. So I'm going to have to switch to the other page since this problem takes up so much room. And so we are looking at this function, g of t equal to 25t over t squared plus 16, and we are looking at the interval from 0 to 40. So the first thing we should do is look at our endpoints. So looking at g of 0, we will have 25 times 0 over 0 squared plus 16, which will give us 0 over 16, or 0. And then g of 40, which will be 25 times 40 over 40 squared plus 16, which will give us 1,000 over 1,616, which I'm going to write this as 0.6188, just so I can get, do an easier comparison. So these are our endpoints. We now want to look for local extrema. So we're going to find the derivative and set it equal to 0. So we're going to find g prime of t, and to do this we're going to use the quotient rule. So let's take the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And we will simplify this. We'll get 25t squared plus 16 times 25, which is 400, minus 50t squared all over this t squared plus 16. Notice I'm simplifying this because I'm going to be setting it equal to 0. And so I want it to be as straightforward as possible. So there's our derivative. Notice that in this denominator, I still have t squared plus 16, and then that squared. This is never going to equal 0. It'll never equal 0. It'll never be negative. This is will always be a positive number for any values of t, but certainly between the values of 0 and 40, which is our interval. So when I go to set this function equal to 0, I know that I have a positive value in the denominator, and the only way a fraction equals 0 and is defined is when the numerator equals 0 and the denominator will not equal 0, which we know is not going to happen. So this function, or this fraction, is going to equal 0 when the numerator equals 0. So I can ignore that denominator and set the numerator equal to 0. And this will give me 25t squared equal to 400. Divide by 25, and I get 16, leaving me with t equal to plus or minus 4. But negative 4 is not in our domain over here. It's not in our intervals, so I'm going to get rid of that negative. This is not, it's not necessary to look at negative 4. So our only other option for a relative maximum is at t equal to 4. So let's put 4 into the function and see what we get. So we'll take 25 times 4 over 4 squared plus 16. And this will give us, let's see, 100 over 32, which is, if we divide both sides, or both the numerator and the denominator by 4, we get 25/8. And this is the same as 3.125. So this value, we're comparing now this to our 0 and our 0.6188. And this coming in at 3.125 is the largest. So this is our absolute max. I noticed that when I was in Newton looking at a problem similar to this, that then asked me for the absolute minimum. So we don't really have to do any more other work. We found our endpoints. Our absolute minimum is up here at 0. This is our absolute minimum.